Okay, we are continuing on in the linear, nonlinear, and mixed effects models module. And today we're going to be talking about nonlinear, non-normal models. And so our first lecture is on nonlinear models. So no required readings for class, but a couple of nice extra readings if you're interested in learning more. And so now we're going to be talking about nonlinear regressions. So a nonlinear regression occurs when your data do not follow a linear trend. So think an exponential function or a saturating function, the second one, or a parabolic function. And it's hard to know what the shape of your data are sometimes, and when you don't necessarily have a linear regression, you have sort of two choices. First, sometimes you know that you have a nonlinear or non-normal data, and you a priori know you need to use a non-standard linear model. For example, if you have exponential growth or a binary response, such as ones or zeros, or count data. If you have those situations, then you're going to think about our next lecture on generalized linear models. But sometimes you don't know what you have a priori. Sometimes you just have data and you don't know if you should use a linear or a nonlinear model. And so that's what we're going to be talking about in this unit. So say you have this data on bacterial colony growth on a medium through time. So you're looking at this data and you're thinking, is that linear? Is that saturating? Is that hump-shaped? I just really don't know. And so you can determine the shape of your data by fitting y as a function of x and trying several different potential functional types. And then you compare your models with AIC to determine which one fits best. So what do I mean by y as a function of x? Well, say you have three potential functions that you think might determine the shape of your data or the shape of x on y. And you can often find these on Wikipedia, the actual shape of, or the formulas for these functions. So if you aren't sure, Google it as usual. So you could have a linear function where y is a function of a coefficient times your x values plus some error. You could have a saturating function where y is a function of a coefficient times x over another coefficient plus x. Or you could have a quadratic function where your data y are a function of a coefficient a times x squared, so your data squared plus another coefficient b times your data x plus another error term. So we're going to focus on these three functional forms. And to do this, we're going to need the nonlinear least squares function, the NLS function in R, and this determines the nonlinear weighted least squares estimates for the parameters of a nonlinear model. And it does this through an optimization process. So you give the NLS function some starting values for your parameters, and it tries a bunch of different combinations until it finds the right one. And you'll see what I mean in a second, but sometimes you don't give it the right parameters and it can't converge, and so you need to sort of play around with what you give it start values. Okay, so what we need to do is run all of our models and compare them with AIC. So we'll first create our model object fit linear, where we run a linear model, which is just y as a function of x, so average colony size, which is y as a function of time. Classic linear model like we did last time. Then you could do a saturating model, and that we're going to call that fit saturating. And here you use the NLS function, and you have your y variable as a function of, and now it's that function we described on the previous slide where we have a times your x variable time over b plus time. And here you have your start list, right? So this is how you start to, the model will optimize finding the correct parameters for a and b, but you have to give it some start values. So again, when I first started this, I picked 0 and 0, but of course that doesn't work for your fraction, and so it didn't converge. So I had to try to pick different values, and so I tried 1 and 0.5, and eventually it converged on values for a and b. So that's how that works. And then say you want to try a quadratic function, so you're going to call that fit quadratic. Again, you're going to use your NLS function, and now you have your y as a function of a times your x variable time squared plus b times time. And so this again looks identical to the equations for a quadratic function that we had on the previous slide. And again, we have to give our parameters a and b some start values. And so once those converge and you have models that fit, we then can use this AIC tab function and compare our three models, the fit linear, fit saturating, and fit quadratic. And as a note, the AIC tab is in the BBMLE library. I just like this one. So, okay, and so what we see based on our delta AIC, so the best fitting model is always going to be a 0, and then this looks at the difference between the AIC values for the best fitting versus the second best versus the third best, etc. And because our quadratic model is more than 5 points, right? It's more than 2 points away from our saturating model. 2 tends to be the cutoff for, like, you could say it's different at 2 AIC points, but again, it's a rule of thumb, so you can't really say for sure, but I can feel pretty confident that if your delta AIC here is greater than 5, that the saturating model fits much better than the quadratic or linear. And another rule of thumb for AIC is that, if two models are 10 AIC points away from each other, then they're really, really different. So here you can say they're different, but not, as different as they could possibly be. So the saturating model fits the best, but as you'll see when we plot the curves with the data, they're still all pretty close. But based on the models we have tried, it appears that the saturating function fits our data the best. And again, in AIC, you're only comparing the models that you actually run. So there could be another model out there that could fit better than the ones we have, but we haven't tested it. So we can only say, given the models we've tried, the saturating function fits the best. So here we'll plot it. And as I mentioned, you can see they all sort of look pretty good, but the saturating function here is in orange. And so that one, according to AIC, is the one that fits the best. And then if you want to run a significance test for all of this to find out if, time is a good predictor of your colony size, you can pull out the coefficients of your model. So here you want to figure out what A and B actually turned out, like what the optimization turned up for A and B. And so you can do that by using this coefficients function for your model object. And so we have A is 17.8 and B is 15.6. And so we just looked at how you can determine if your coefficients are significantly different from 0, but if you want to find out if your x variable time predicts your y variable average colony size, you can actually fit your nonlinear function into a linear model by defining the function as we did with the NLS. But you actually then take your parameters A and B and fit them into your model. So what you would do then is, so you pull out your coefficients from your model, and then in your data set you can create two parameters, A and B. And so you can pull out coefs1 is going to pull out the first value for A, just the value for A, and that you're going to put that into your data set, and then you're going to pull out your coefficients for B, your coefficient for B, which is you get by doing coefs square brackets 2. And then you define your model here, the linear model, as y, which is the average colony size, as a function of A, which is now a number, times, it's like 17, times time divided by B, which is, again, a number, about 15, plus time. And then you do an ANOVA of your model, of this model, this linear model, and you can see that time is a significant predictor of your colony size. And if this is a lot to look at the code, so I would, if this is at all confusing, I would recommend looking under the hood, getting the data, trying it out, seeing what this actually does, so you can see how really nice some of this coefficient function is and how easy it is to pull these values out and fit them into your models. And so with that, please complete quiz 5.1 on Canvas and continue on to the next lecture.